So first question we're going to look at is transformations of exponentials. So the first thing we want to do is identify how many different transformations it would take to turn g of x, which is our starting function, into f of x. How many transformations would it take? Yeah.
3.
Yep, it's going to take 3 transformations. And what's the first thing we would focus on? The minus, the plus 1, or the minus 4? Yep.
The plus 1.
Yes, plus 1. So that's a plus 1, and it's inside the exponent. So what kind of transformation is it, and which way is it going to move? Yeah.
Is it horizontal shift left 1?
Yep, that's going to be a horizontal shift left 1. Okay, so there's the first transformation. What are we going to look at that tells us the second transformation? Yeah.
What's in front of the 3?
Yeah, what's in front of the 3? In that case, we have negative. And what does a negative in front do? Yeah.
Reflection.
Yep, it is going to be a reflection. And there's 2 kinds, so can you tell me which one?
A vertical reflection.
Yes. So vertical reflection. You could also say reflect over the x-axis. Yep. So vertical reflection. And then that leaves the minus 4 as the last transformation. What is the minus 4 going to do? Yeah.
Shifts the graph down 4
Yep.
units.
So that's a vertical shift down 4. And that's how you describe the transformations. Now, there's going to be another question that's giving you a graph, and you're going to have to match it with the ones that I give for choices. So to do that, you just have to know how to sketch that on the calculator. So let's combine that question with this one. So when we type that in, we've got negative 3, and we've got to the x plus 1. Shouldn't need any parentheses around the x plus 1 because the calculator will handle that as the exponent. Just make sure the minus 4 is outside it. Only thing I'm wondering, yeah, that should be okay. So normally when we graph an exponential, it's going to go like that. That's an exponential growth. This has a couple shifts, so that's going to change it a little, but this is the one that's going to make it change a lot. It's going to be a vertical reflection. So that means the graph should look more like that. So let's graph it and see if that's what we get. Let's do zoom 6. Should curve down. Yeah. And again, there's a couple other things going on because it's been shifted, but it does curve down, and that's what we expected. All right. So what you'd have now is I'd give you different choices, and you'd have to match that graph to one of the choices. So any questions on how I type that in? No? Okay. All right, so next one we're going to look at is describing, looking at an exponential function and describing if it's growth or decay. And the key is looking at the base. So let's start with f of x. Anyone think they know if that one is growth or decay? Matt?
Growth.
Yeah, that's exponential growth. And how do you know?
It doesn't have a negative exponent, and it is a number that is not a fraction.
Well, if it was a fraction like 5/3, that would still be growth.
Well, it is not a fraction where the numerator is bigger than the denominator.
Yeah, it's not a fraction. So let's just say it's a base bigger than 1.
Yeah.
Yeah. So if the base is bigger than 1, it's exponential growth. Yeah. Growth is going to look something like that. There's your graph. Okay. How about g of x equals 1/3 to the x? Yeah.
Decay.
Yep. That's going to be exponential decay. And that's because the base is between 0 and 1. Exponential decay is going to look like that. Okay. Now you could reflect it or flip it, but I'm talking about this one in particular. It's going to have that look to it. And how about h of x? 4 to the negative x. Is that going to be growth or decay? Yeah?
Decay.
Right, that is going to be decay because when you rewrite that, the base is really not a number bigger than 1. How would you rewrite that? So we had a positive x as the exponent and not a negative x.
1/4.
Right. That negative causes the base to flip. So that's really a base of 1/4, which is exponential decay. And that one's going to look like that. Okay, let's look at that last one, h of x. If I ask you to describe the end behavior, what if I wrote down as x approaches infinity, what does h of x approach? And I put h of x because that's the name of this one. As x approaches infinity, what does h of x approach? And pretend that these are your x and y axes right here. Just like that. Yeah.
Infinity.
Nope, it's not. That's not approaching infinity as x approaches infinity. As x approaches infinity means we're going which way on the graph? To the, yeah?
It's going to the left.
No. Yeah?
It's going to the right.
To the right. So as x approaches infinity, that means we're going to the right. So what happens to the graph as you approach infinity? It approaches something, but it doesn't reach it. Yeah?
0.
It's approaching 0. Yeah. Now let's look at the behavior the other way. Okay. As x approaches 0, what happens to h of x? So now this is as x is approaching 0. And normally we look at approaching a number from both sides, but you can't because the graph doesn't exist on the other side of 0. So you can only look at it approaching from the right. Yep.
Does it approach infinity?
It approaches infinity. Yep. So that's how you would describe the end behavior. And that would be pretty typical of a decay graph that hasn't been reflected or anything like that. As you go to the right, it approaches a number, in this case 0. As you go to the left, it approaches infinity. So any question on describing something as growth or decay, and then describing the end behavior? Okay, the other thing I just want to make sure I put in the video, I had put down the topics that we were going to do logarithmic transformations. That's not till section 5.5. So those are not on the test. All right, so the next question we're going to look at involves solving an exponential inequality. So it's the approach we're going to do is we're going to graph each one of them, and we're going to look where the 2/3 to the x is above 1/3 to the x. All right, and we're going to write our answer as an interval. Okay. So I've already graphed each equation. To graph them, this is what you would want to type in. And because the 2/3, that's the blue one, we're looking for where the blue one is above the red one. Okay, so let's look at that. First of all, let's make sure that even happens. Is the blue one ever above the red one? Yeah. There's a point where the blue one is under, and then there is a point where it switches and it goes above. What do you think we're going to have to calculate using the graphing calculator here? And again, this one might be kind of obvious, but just in case it was shifted, we would want to calculate this. Yep.
Maybe the intersects.
Right, we want to find where they intersect. So second calc, intersect. Because they only cross one time, we don't have to be careful about where we put the cursor. But they do intersect at the point 0, 1. Okay, so now, remember you're solving for x. Where is the blue graph above the red one? For what values of x? Yeah.
When x is greater than 0.
Okay, so if you write your answer as an inequality, x is greater than 0. Yep, the blue one is above. How would you write that as an interval? Lauren?
0, infinity.
Anything else we need?
Parentheses.
Yes. Why would you put a parenthesis on 0?
Because it has to be greater than, not greater than or equal to.
Right, it has to be greater than. And why a parenthesis on infinity?
Because you can never reach infinity.
Could never reach it. Perfect. All right. So that's how you would solve an exponential inequality graphically. Okay, so next question we're going to look at is an exponential word problem. So for the test, you could have growth or decay. This one is a decay problem. And it could be a particular percentage I give you, or it could be like a half-life problem, which in that case, you already know your percentage is 50. All right, so they're both similar. It's just this is just a random percentage, where half-life is a fixed number. You'd always use the same one. All right, so in 1990, we had 10,000 people in the town, and it's going down at 3% every year. So the first thing we need is a formula. Okay, we need our population as a function of time. When you write an exponential decay formula, what's the first thing that comes after the equal sign? Yeah.
The initial population.
Initial population, which in this case is 10,000. Now, if it was a half-life problem, we already know what to put inside there. We would just put a 1/2. This time it's not, so we have to figure out what goes in there. What do you always put inside the parentheses for decay? Kelsey?
Well, and I think I was thinking growth. I was going to say 1 plus r, but that's not.
So 1 plus r would be for growth, which is still a good one to know. That definitely could be on the test. Yep.
1 minus r.
1 minus r. And what's r in this case? Yeah.
0.03.
Yeah, so we're going to make sure we change that percent to a decimal. And one more thing we should do, because without this, it's not an exponential equation. Yeah.
Like t is an exponent.
But the t is the exponent. Okay. So there's your problem or there's your equation that models the problem. Now it says find the population in 2025. To do that, would we be plugging in a number for t or p of t? Yeah.
T.
We'd be plugging a number in for t. What number how would you figure out the number you have to plug in for t? Yeah?
You would subtract 2025 from 1990 to figure out how many years.
1990 from 2025.
Yeah.
Because you got to figure out how many years has gone by. That's what you plug in for t. So how many years is it to get from 1990 to 2025?
35.
35 years. So that means this population is going to have decreased 3% for 35 years. Okay, so let's figure that out. So our population is, and I'm going to fill in our population after 35 years is 10,000 times 1 minus 0.03, let's just simplify to 0.97, raised to the 35th power. Okay, so this is going to tell us about how many people would be left in the town after 35 years. So let's do 10,000 times 0.97 raised to the 35th power. So we'll have gone from 10,000 people, we'll just round to the nearest person. So what would that be properly rounded to the nearest person? Matt, yeah.
30,444.
3,444. 3,444 people. Yep. Okay, so we filled in for the time, we solved for the people. Now we're going to fill in for the people, solve for the time. So this 9,000 is going to get plugged in on which side of the equation? Yeah, maybe.
The left.
Yeah, it's going to get plugged in for the left. Now, once I do that, we can decide, do we want to solve it with a logarithm? Or do we want to solve it by doing like an intersect, which we've kind of already done the intersect stuff. So do we want to solve it with a logarithm or intersect? Which way do we want to do it?
Will it matter for the test tomorrow?
No, you'll be able to do it either way. Yeah? Graphing it? Okay. So if we want to graph it, then what would we put in Y1?
9,000.
We're going to put 9,000. Okay, how about Y2? Yep, 10,000 times 0.97 to the x. Now we're going to set our window. What would be a good value for x min? Yeah.
Oh wait, hold up, I'm blinking really hard right now.
Remember, x is taking the place of t.
Probably like 1990, just in general. Just like right there. But that was taller enough.
So what's x again? It's the time. So what's the smallest amount of time that could go by? That would be your x min.
1 year.
We could have less than a year. Could have less.
0 times.
0. Yeah. If no time goes by, then the population is 10,000. And the most time that goes by, well, we know by the time we get to 35 years, we're down to 3,444 people. So we're going to be down to 9,000 people way before that. I don't know how much. Maybe it happens within 8 years. If that's not enough, we'll fix it. How about my Y min? What would be a good value for that? Yep.
0.
Okay, we could look as low as a population of 0. We don't really have to look for the population getting all the way down to 0, even though it never reaches 0. We only have to see when the population gets down to what? 9,000. So I would probably do 8,000 for the Y min. And for the Y max, well, what's our starting population? 10,000. So there's no reason to look above that because the population never goes above it. So you should see a line and then a curve coming down. Let's see. Oh, there's your line. And your curve is going to start in the upper left. And it's just a question if we zoomed out far enough. Yeah, looks like we did. Now that looks, it looks pretty linear. It's not. It is an exponential, but it's 0.97. So this is going down so slowly, it's hard to see the curve without zooming out more. But that red line is a curve. Does anyone want me to zoom out more so you can see it, or believe me? Okay, yeah, it's a curve. All right, so let's calculate the intercept. And that gives us about 3.46 years. Now, that's 3.46 years. So what year would that actually happen in our problem? Somewhere during the year of what? Yeah?
1994.
Yeah, somewhere during the year of 1994, because you're going to have to go through 3 full years. So that's 90 to 91, 91 to 92, 92 to 93. That's 3. And then you're like halfway almost into the 4th year. So yeah, it'd be somewhere between in 1994. All right. So any question on solving it that way? All right. Okay, so this is another example of an exponential equation that we're going to solve. And there's a couple ways we could do it. I want to try to do this one algebraically. Okay, so we could graph it, but let's try algebraically. What makes that one a little bit more complicated is the negative on the exponent. When you have a negative, okay, what does that mean? Like if I wanted to rewrite that without a negative, we kind of did this when we talked about growth and decay.
Wouldn't the base flip?
Yeah, so what would the base be?
1/3.
Okay, so it would be 1/3 to the x equals 4/5. Yep. Now we have to get x by itself. So to get x alone in this one, the problem is it's a variable. So it would be great if we could somehow move that x so it's not a variable, not in the exponent anymore. But you can't just take x's and move them. The only time you can move them is if there is what function in the problem? Yeah.
A log.
Right, you have to have a log. So let's take the log of both sides. Log 1/3 to the x equals log 4/5. Okay. Now, because that exponent is a variable on an argument to a log, what can you do with the x? Yep.
Move it in front of the log.
Yep, you can now move it in front of the log. So you have x times the log of 1/3 equals log of 4/5. And lastly, now how would you get x by itself? Matt?
Divide by log of 1/3.
Yeah, divide by log of 1/3. So those cancel. And that's your answer. Now, when I took the log of both sides, I didn't write down a base. So what base does that mean we assumed we were using? Yeah.
10.
10. I could have taken the ln of both sides and I would have gotten the same answer. It doesn't really matter. Okay? It just has to be a base that I can do on the calculator easily. So let's type in log 4/5 divided by log 1/3. Now if you used ln, let me show you what would happen. ln 4/5 divided by ln 1/3. It wouldn't have mattered. Okay? It's the same thing. So we get 0.203. Now, if we want to check that that works, what could we do? Yeah.
Would you plug it in for x?
Yeah, just plug it in for x and see if you get the right answer. So take 3 to the negative 0.203. So take 3 raised to the negative 0.203. I'm even going to go a little bit more accurate. 203,114. And I get what do I basically get? 0.8. And if you take 4 and divide by 5, that's 0.8. Yeah. So that's how you can check your answer. All right, so that's solving an exponential equation. Okay, so the next question looks at special properties of logs. The first group of properties we did, there were 4 of them. And I think this was the 3rd or 4th one in that group. So it's asking about log base 8 of 1. When you take the log of 1, it doesn't matter what the base is. You always get the same answer. What is the log of 1? Yep.
0.
0, yeah. Because this is basically saying 8 to what power would give you 1? 8 to the 0 power would give you 1. Okay. Now, another property that we studied were the ones from today. Those were the 3 about the combining and the splitting. So let's look at like log base 3 of x squared times y, let's say divided by z. And the directions here are to split into multiple logs. And I want to make sure that we express exponents as factors. That means don't leave an exponent in the final answer. Okay. So express exponents as factors. Now this kind of problem, I could have done it two ways. I could have either given you one that was already split and you could combine it. In this case, I'm giving you one that's combined and I want you to split it. Okay, but both ways are important. All right. So what's the first thing we're going to do is we're going to split this up into two logs. Are we going to deal with the multiplication first or the division? Yeah.
The division?
Yeah, deal with the division first. So we're going to have two logs. What's going to be the base on each of them? Yep.
3.
It's going to be 3. It was division, so that means when we subtract, it was division, so what do you do with the two logs? You subtract them, yeah. So we're going to subtract the two logs. What's going to be my first argument? We still got more to do with it, but we'll just leave it for now. Yeah.
X squared times y.
X squared times y. And what's going to be my second argument? Yeah.
Z.
C. Okay. So we still haven't done everything they wanted. We didn't express the exponents as factors yet. One of these logs is done. Which one can we not really do anything else with? Yeah.
The one on the right.
Yeah, log base 3 of z, that's all you can do. So that one we can just kind of copy down. But this one, we still have something else we need to deal with. We have this multiplication. That's going to split up, this part that I just circled, into how many more logs? Yep, 2 more. Okay. We're going to have a log base 3, another log base 3. And what are we going to do with these 2 logs? We're going to add or subtract, Matt? Yeah, we're going to add them up. Now, just one step at a time, what would this first argument be right here? Yep.
Oh no, X. Well, it would be X to the second.
It would be x to the second, but then what happens with the 2?
You'd put the 2 in front of the log.
Put the 2 in the front. Yep. And then what would be my argument to my second log? Yeah,
Why?
y. And that is as much as you can do to split this up. Any questions on how we split that into multiple logs? Yeah,
You always want us going as far into splitting them up as possible, right?
yeah,
Okay.
yep. The other thing to remember is if you did have something like this, and I said to write that without any exponents, that does have an exponent. It's hidden. What did we say that the exponent was on a square root? Yeah,
1/2.
yeah, it's a 1/2. So I'm not saying that'd be the whole problem, but that might be in part of the problem, and you'd have to fix that root. Okay. All right. So these are the other 4 special properties of logs that you would need to know. And these are, when I referred to the 3 properties, how to combine logs and split logs, and the property that allows us to put a number in the front of a log. All right, so this question says to solve for x, and it's a log equation. There's really only one thing we've learned how to do so far with log equations, and that's what?
Convert them to exponential function.
Yeah, convert it to exponential. Okay, so there are 3 things that we need when we write it in exponential form. We need a base, an exponent, and then something on the other side. What's the base in this problem? Yep.
10.
10, yes. So So you would have to know the base is 10 because it's not root. What about my exponent? Yeah,
That'd be 4.
4, because logarithm always equals the exponent. And what do we call this right here? The x, yep.
The x in the logarithm is the argument.
It's the argument, and the argument ends up by itself. And that's it. Once you rewrite it in exponential form, that is your answer. 10 to the 4th power would be how much? 10,000. There you go. So that's converting something from log form into exponential and then solving. All right, so this one says to just evaluate log of 32. Is that one that the calculator can do? Yeah. What's the base on that log? 10. So all you have to do is press log of 32. That's a very, very easy one. Right? Say 1.51. Okay. How about log base E of 16? Is that one the calculator can do? All right. How would I type that one in on the calculator? Yeah.
ln.
Yeah. ln of 16, and we get 2.77. All right. How about this one? Log base 3 of 14. Is that one that the calculator can do? No, we don't know how to type a base 3 in, but we did have a problem today where the base ended up being a number other than 3. So if you put just temporarily, let's just put equals x. If you rewrite this in exponential form, it's not really going to help you right away, but it might eventually. What would this be if you rewrite it in exponential form? Yeah.
3 to the x equals 14.
3 to the x equals 14. Now, what is the problem with that that's making it kind of hard to solve? This is the reason why you wouldn't see that in Algebra 1. Yeah.
The variable is the exponent.
Right, the variable is the exponent, so we don't want that variable as the exponent. It would be great if we could somehow get rid of that as an exponent. And we can, but what do we have to do? Yeah.
Take the log of both sides.
Take the log of both sides. And now that we've taken the log of both sides, what can we do with that x? Yeah, Lauren.
Move it to the front.
Move it to the front. So now you have x log 3 equals log 14. And now to get x by itself, what would we do? Matt?
Divide by log of 3.
Yep, divide by log of 3. So we talked about this today, and if you recognize this pattern, that's what always ends up happening. Basically just ends up being log of this number divided by log of this number when you have that type of equation. If you don't remember, that's fine. You can do this every time. But that's the pattern. Okay, so last question. We're going to be finding a power model for this data. What's the first thing that I have to do with that data in order to find a power model? Yeah.
Plug it into a table.
Yeah, we're going to put it all into the table. And you got to press stat, and you have to go to edit. That's where you have to type it in. So we're going to put in 1, 4, 5, 13. And again, you'd be given all that information on the test. 5, 14.1421, 16.7185, and 13.34, whoops, 34.2316. You have to make sure you have the same amount of numbers in L1 and L2. If you don't, that's like writing a coordinate without the X or the Y. You're going to get a weird error. Okay, so you got to have 4 numbers in each column or 5 numbers, however many they give you. Okay, we got all our data typed in. What do we do next? Yeah.
You press the stat button again.
Mhm.
And then from there, we need to go to calc. And
to calc.
it's underneath the letter A, but it is like the short for the power model.
Yep. So we're going to go to option A, which is power regression. Hit enter. Did I put my X's in L1 and did I put my Y's in L2? Yeah, then there's nothing we need to change there. So what do we do now? Yeah,
Click calculate.
let's calculate. And remember, we want to round these answers appropriately because those are all approximations, so are those. If we round A appropriately, what would A round to?
5.
Yeah, so this should be 5. The only reason it's not 5 is because we don't have 1 decimal accuracy. And B should be rounded to what number?
0.74. Or 0.75.
0.75, right? It's 0.7499997. It's very close to 0.75. If you write 0.75 or you put 3/4, I'd accept either answer. So it's 5 is the A times X, and B is your exponent. That's what that little symbol right there means. That's exponent. 0.75. And that's the equation of the power model that would go through those data points.